Have you ever really stopped to think about what sound is? I mean, what's actually happening? Today, we're going to pull back the curtain on the physics of it all. We're going to explore the hidden properties that define every single sound you hear. Let's get into it.
Right? I mean, what is the actual difference between a whisper and a shout, or a deep, booming drum and a high-pitched whistle? It's not magic, it's just physics, and it all comes down to these invisible waves moving through the air around us. Today, we're going to make that invisible world visible.
So, even though we can't actually see sound waves with our eyes, we can describe them, we can measure them, and we can understand them with, honestly, incredible precision. And it all starts with their basic building blocks. And here they are. These are the three pillars of sound: amplitude, frequency, and speed. If you can get your head around these three concepts, you basically have the keys to understanding any sound in the entire universe.
So let's do it. Let's dive in and break these down one by one. And we'll start with the one that separates that quiet whisper from a loud shout.
First step is amplitude, and it's actually super simple. Amplitude is just the height of the sound wave. If you were to draw it out on a graph, a taller wave literally just means it has a bigger amplitude. So what does that mean for your ears? Well, a wave with a low amplitude, a shorter wave, gives you a soft, quiet sound. But a wave with a high amplitude, a really tall one, creates a powerful, loud sound. So long story short, amplitude is just loudness. That's it. Okay, next up is frequency. This one's all about timing. It's how many full waves, from top to bottom and back again, pass by a certain point in just 1 second. You can think of it as how bunched up or spread out the waves are. And of course, we have to measure this somehow. The unit we use for frequency is called hertz, which we just shortened to Hz. So whenever you see a number with Hz after it, you know they're talking about frequency. So, a low-frequency sound has fewer waves passing by each second. They're more spread out. A high-frequency sound, on the other hand, has a ton of waves all packed tightly together. Now keep that difference in your head because it's going to be really important in just a minute. And our third key characteristic is speed. And yeah, this one is pretty much exactly what it sounds like. It's just how fast a sound wave is traveling from whatever made the sound to you. And just like the speed of a car, we measure the speed of sound in distance over time. The standard unit that scientists use is meters per second. Simple enough, right? Okay, so now that we've got the big three characteristics down, let's zoom in a little closer and look at the actual shape of one of these waves. Think of this as a quick lesson in wave anatomy. Every single wave has a high point, kind of like the peak of a mountain. In physics, we call this the crest. It's the point of maximum oomph, the highest that wave gets. And, you guessed it, for every peak, there's gotta be a valley. The lowest points of the wave is called the trough. So we've got the crests at the top and the troughs down at the bottom. Now, if you were to measure the distance from one crest to the very next crest, or from one trough to the next trough, that distance is the wavelength. It basically tells you the physical length of one complete wave cycle. All right, remember how I told you to keep frequency in mind? Well, this is the payoff. This is where it all connects back to something we all know from music and just talking, and that's pitch. And here it is, the big reveal. Pitch, how high or low a sound feels to us, is 100% determined by its frequency. They are two sides of the same coin. You change the frequency, you automatically change the pitch. It's a really direct relationship. A low frequency, with those lazy, spread-out waves, gives you a low pitch. Think of a deep, heavy voice or a bass guitar. But a high frequency, with those waves all bunched together, creates a high pitch, like a thin, shrill voice or a flute. Okay, so let's put all the pieces together now. How do these individual ideas combine to create the, rich and complex world of sound we live in every day? So here's the recap. A wave's height, its amplitude, that just tells you its loudness. A wave's, its speed of vibration, its frequency, that tells you its pitch. And the other parts, the crest, the trough, and the wavelength, they just describe the wave's physical shape. That's really the whole shebang. So the most crucial point to take away from all this is that the invisible world of sound isn't some great mystery. It is perfectly, totally measurable. And these measurements are what explain everything from the quietest little hum to a huge, loud bang. It's all just physics in action. And I'll leave you with a final thought to chew on. We know sound travels at different speeds through different materials, right? Like air versus water.
So, knowing everything we just talked about, what do you think happens to the pitch of a sound when it travels underwater? It's a really interesting puzzle, and the answer is built directly on the concepts we've explored today.